Good evening, everybody. This is Chris Morisette, the Novice Chair for HAS. Um, I'm going to be presenting the October Novice meeting via recording. I'll be, at this point in time, I'll be up in Colorado getting some fresh mountain air and cooling off from this horrid summer that we just went through. So um, I appreciate the opportunity to still speak in front of you, even though I'll be up in Colorado. Um, as usual, as you get questions during the course of the meeting, please put those in the chat. And Joe Caleb will be hosting tonight. Will answer those on my behalf, or get with me after I get back, and I'll provide any follow up that's necessary. Okay, so I think we've got a really great meeting tonight, navigating the autumn sky. A lot of great objects in the autumn time frame, and I've hopefully picked out some really good ones to go over with you tonight. The topics for tonight, we'll just do a quick refresher on navigating the night sky. We'll talk about autumn signposts, what you can use in the night sky in order to find your way around and find these objects that we're going to be talking about tonight. We'll then do a tour of several that objects that I think are just fantastic. Um, I'll have a supplemental presentation at the end on space observatories, uh, kind of a short, sweet by the numbers discussion. Uh, and then I want to wrap up with a few words about the novice presentations for 2024. Okay, so navigating the night sky. Um, I don't have the October map, unfortunately, since I'm recording this earlier in the month. So the September map is here for your use. Um, Here, as we typically show, we are able to look at the night sky as we're facing south. And this is the orientation of the map that you would have. And you can see the various constellations. Notice the position of the summer triangle. Again, this map is about 8 o'clock for early October, and you'll notice that the summer triangle is high in the sky, and that's important because we'll be using that. If you're facing north, you take the map and you turn it 180 degrees the other way, and that's the view of the night sky that you'll have in front of you. Remember our celestial coordinates. Again, right ascension being analogous to longitude, declination being analogous to latitude. The ecliptic runs at an angle to the celestial equator, and there you'll find the sun, the moon, and the planets. Here's another depiction of the various equators that are out there. So the celestial equator, which is where the stars rotate around, that will be our primary area of interest. The ecliptic is at about a 23-degree angle from the celestial equator, and then the galactic equator is about 63 degrees from the celestial equator. Here's another view that I really get a kick out of. It shows the our solar system and our orbit of Earth around the sun with respect to the Milky Way. So here you can get a good idea of what the orientation looks like, and you'll notice also that the Milky or the solar system is actually traveling around the Milky Way. So again, just another pictorial to kind of get you oriented on where we're at and where things are in the night sky. These are important. The signals that allow you to measure distances, pinky being 1 degrees, Scout's honor being 5 degrees, fist being 10 degrees, hook'em horns 15 degrees, and then the Hawaiian sign for hang loose at 25 degrees. And again, if you're out in the night sky and you're navigating naked eye or with binoculars, knowing these distances and how to use your hand to measure these distances is very useful. All right, so we'll talk about autumn signposts. Now, in the spring and the summer, we relied on heavily the Big Dipper to allow us to, move around the night sky and find various constellations, objects, etc. And during the spring and the summer, that worked out really well for us because the Big Dipper was up high in the sky. As we move into autumn, the Big Dipper is not going to be as useful to us as it was in the previous two seasons. And that being because it's going to be down here lower on the horizon. We really utilize the handle and Arcturus and Spica to get to a lot of different objects in the sky. And since it's so low on the horizon, unfortunately, we won't be able to do that. So so that's not good, but it's not going to be a deal killer for us because we can rely on the summer triangle. And summer triangle, fortunately, is easy to find, and the summer triangle can get us to a number of different spots in the night sky. The summer triangle is going to be our main signpost for moving around the night sky here in the autumn. Here's our map of the night sky, and you'll notice the green boxes here on the chart. This will be our area of interest. So I have about 6 degrees of right ascension, or 6 hours rather, excuse me, of right ascension blocked off here. And here is where our area of interest in viewing is gonna lie, and you'll notice that the summer triangle is right on the edge, but still a very useful signpost for us to use. Okay, so with that in mind, let's go ahead and dig into these autumn sky objects for the autumn sky. And again, I think a really great lineup of objects that we'll be talking about today. So here, we'll start out in Cygnus, which Deneb, the kind of the main brightest star of Cygnus, is one of the points on the summer triangle. And so if you can find Deneb and you can find Cygnus, you can find these objects. So we'll be talking about the Veil Nebula, the Crescent Nebula, and the North American Nebula. So here is the Veil Nebula. One of the most striking and beautiful objects I personally find in the night sky. What you're seeing here is actually several nebula that constitute what they call the Cygnus loop, and the two main nebula that you see here are the Eastern Veil Nebula down here and the Western Veil Nebula up here. And what you're looking at is the remnant of a supernova. And it's really striking because you can almost kind of see waves and patterns that would be similar to maybe lightning or something like that. And that's because you've had such a cataclysmic event where a star went supernova and the remnants of that star getting blown out and disturbed by the shock waves from that explosion or implosion. It's really a striking feature. This supernova is about 12 degrees below Deneb, and that's how you can find the position of this object. It's about 2,600 light years away from Earth, and the two nebula that I just pointed out, the Eastern and the Western, the Western nebula, Veil Nebula, is about 53 light years in length. The Eastern is about 100. And again, here's the Eastern, here's the Western. And again, it's a very cool looking object. The star that had created this supernova was about 20 times estimated to be about 20 times larger than our own sun, and the um, the uh, the hypothesis is that this supernova was bright enough to be seen during the day when it occurred. So um, again, it's a beautiful object. It's an important object because it demonstrates, you know, the end of life for a star, and one that's well worth trying to go out and find during the autumn time frame. The next object on our Cygnus list here is called the Crescent Nebula. This is right at the star Sadar, and if we go back up and look, it's Sadar's is the middle star right here in Cygnus. So if you can find that star, you're right in the ballpark for finding the Crescent Nebula. Now, this nebula is a real oddball. It kind of to me reminds me of the human brain if you look at all the waves and in the general shape of the object. It is actually formed as a result of fast stellar winds from a Wolf-Rayet star, which is the middle star here that you can see in the center of this nebula. There are stellar winds that are emanating from that star, and they're colliding with and merging with the slower moving winds that were ejected originally by that star. So you'll see this collision, and I believe these bands here and here are kind of the manifestation of that collision. It's an interesting. It is an emission nebula. It is not a supernova remnant, but it is very interesting looking. It's a relatively small object. It's only about 32 light years in size, and about 5,400 light years from us here on Earth. But it is a very unique, a very interesting nebula to go take a look at here. So that's the Crescent Nebula. Really interesting stuff there. The next one on our list is the North American Nebula. Again, the North American Nebula is another emission nebula. This is kind of a wide field view of that nebula. And you can kind of make it out here in the middle, excuse me, of the nebula. And if we go down here to this next picture, you can see it in more of its glory. So the North American Nebula is right at Deneb. So this is a relatively easy one to find. It's a very wide field. This object has a very wide field of view, but it's but the surface brightness of it is very dim. So it's not an easy object to pick up with binoculars or a small telescope. As a matter of fact, I'm not sure you probably would be able to pick it up with binoculars, but it'd be very faint. This object has a couple of features here that are worth pointing out. So that it gets its name North America because you can kind of see here the Gulf of Mexico and the North American continent. This area here, which you would look at and say, well, that's Mexico and Latin America. This is a region that is called the Cygnus Wall. Again, it's another feature that is something that a lot of people go out and try to view and photograph. And so that is a subset of the North American Nebula, but it's right in this area right here. Very cool looking. Okay, so those are three really cool objects that are right there in Cygnus and the Summer Triangle. We're now going to go to a little bit different position in the sky, a little bit farther down or south, as they say. And we're going to go over and look at the Helix Nebula. Now, in order to get to the Helix Nebula, we're going to have to try and go back to our old friend, the teapot, from as a summertime signpost, and we're going to use that to get over to the Helix Nebula. So we're going to remember, if we can find the teapot is kind of down at an angle from the summer triangle for you. So you find the summer triangle, you follow the Milky Way down to the horizon, and you'll be able to see the teapot, and you still should be able to um, uh, see and make out the teapot during the autumn. It's going to be probably gone, earlier in the evening than it was in during the summer, but we still might be able to take advantage of the teapot. So if we can locate the teapot, what we want to do is go to the spout of the teapot, which are these two stars. And then what we want to do is follow a line from those stars about 40 degrees off to the left or towards the handle of the teapot. And that's how we'll get to the Helix Nebula. Is by lining up these two stars on the teapot, using that to get our bearings or our direction, and following that about 40 degrees off to the left. And when we do, we'll come to the Helix Nebula. And the Helix Nebula is it's one of the larger planetary nebulas that are out in the cosmos, and one of the most gorgeous planetary nebulas. Again, if you remember from past discussions, excuse me, planetary nebula is what you have. It's the remnants of a star that has died, come to the end of its life, and that star would have been roughly the size of our own sun. So that's what we're looking at here with a planetary nebula. And it is referred to as the Helix Nebula because if you look down inside of this, you'll begin to see that twisty, turny kind of shape that you see with a strand of DNA. In this particular picture, it's not as apparent as it is in other pictures, but you still might be able to make out that twist or that turn of the structure in the nebula. This nebula is about 790 light years away from us, so it's relatively close, and it's only about 3.4 light years in size. So in order to see this, you're going to need a larger telescope, and you're going to need some dark skies because it is going to be small, and it's going to be faint as well. But one that's definitely worth the effort to go see because it's really, really a beautiful planetary nebula. Next, we're going to turn our attention to some galaxies. We're going to be looking at a couple of galaxies or groups of galaxies. So we've got Stephan's Quintet and Andromeda. Stephan's Quintet is up in Pegasus, and it is located between a couple of stars, Matar and Peg, up here. We'll look at that one first, and then we'll go down here and look at Andromeda. And with Andromeda, what we'll be in the Andromeda galaxy, and we'll want to come off of Alpheratz down around on this lower branch of Andromeda, and then up, and we'll find it right here. I know this looks a little complicated, but it's not as bad as you might think. I remember last autumn, excuse me, being out at the dark site with my binoculars, I was able to traverse this and find this object very easily. Following these two arms, once you get your bearings on these arms, which are relatively easy to find, you can find Andromeda. And Andromeda showed up very nicely out at the dark site with a pair of binoculars. So let's go and look at Stephan's Quintet first. So this is a group of 5 galaxies, and it's referred to as Hickson Compact Group 92. The 5 galaxies are here, here, and here. And in this group, you'll notice that this larger galaxy is a little bit different from the others, and it's actually not it's not in the group per se because it's much closer to us than the other two. So, or the other four, excuse me. So the other four galaxies are about 320 million light years away from us. This galaxy here that's in the foreground is only about 75,000. I'm sorry, it's only about well, I don't have the figure here. I apologize, but it's much closer than the 320 million light years from us. And so, but they are referred to as the quintet. And then the brightest one is the one here in the foreground. This is NGC 30 or 7320, and it has extensive regions of H2, which is indicative of star forming regions. In this particular picture here, it's tough to make these out, but if you blow this picture up, you can actually make out these regions down here and here. So for a galaxy that is as far away from us as it is, and again, I apologize for not having that distance here. If memory serves me, I think it was more like in the um, 40 to 50 million light year range. But again, I'd need to go back and look at that. But given how far away that galaxy is, to be able to make out the H2 regions is really remarkable. Okay, so that's Stephan's quintet, and again, this is a very small object, so you're going to need to have a pretty large telescope in order to go after that one. Next is Andromeda, probably one of my favorites, not only because it's beautiful to look at and easy to find and just kind of stunning in general, but it has such a cool history behind it. And so here's Andromeda. Andromeda is about 2.5 million light years from us. It's the closest spiral galaxy to us, and it is actually larger than the Milky Way by about a third. So it's about 130,000 light years across, and we're about 100,000. So it's a marvelous, striking object to see, and it's very accessible to see it too. So with that in mind, let's talk a little bit about the history, because the history is it's just fascinating here. This galaxy was thought to have been what they call a spiral nebula, and people thought it was because it was so large in size. It has about the same field of view as 5 full moons, so it's a very large um, object, and the um, the thinking is that this object here is in our own galaxy. It's close to us. It's just a very large object. And Edwin Hubble was the astronomer that was able to really determine its distance from us as being much farther away than people had estimated, and really brought to light that the Milky Way is not the universe. It's that the universe extends far beyond the Milky Way. Now, in order to determine these distances, he used variable stars in order to make that determination. I think Cepheid variables is the exact term for it. And as luck would have it, the variable star that he discovered, which allowed him to determine these distances, he discovered on the evening of October 5th, 1923. So, as you're watching this recording, exactly 100 years ago tonight is when he made that discovery. And I think that's pretty cool. And again, that really opened up the horizons with respect to modern astronomy. We were no longer bound to the Milky Way, and there was a much larger universe at play out there. A couple other things about M31 Andromeda. It has a couple of companion galaxies, and I just want to check my notes, make sure I get this right. I think M32 is this galaxy right here, and this one is M 110, if the memory serves me right. In either event, this galaxy right here, this companion galaxy, is thought to have passed through the disk of Andromeda, and as a result, it had an interaction with Andromeda and actually warped or deformed the spirals in the main disk. So um, that's pretty interesting feature of this galaxy and its two companion galaxies. Also, Andromeda is moving towards Earth, moving towards the Milky Way, and at some point in time in the distant future, we're going to merge with Andromeda and become one galaxy. So that's Andromeda, one of my favorites, and very easily accessible. It could be viewed naked eye at a dark site. Definitely can be viewed with binoculars. I've even seen it from my driveway here in light polluted Kingwood. So it's really cool. We're going to move on next to Triangulum, or the Pinwheel Galaxy. This is another galaxy that is in our local group. Andromeda, the Milky Way, and Triangulum are all part of the local group of galaxies. And in order to get to Triangulum, we move a little bit to the left and downward into the constellation of Triangulum, and there we'll find M33. This is a gorgeous picture of M33. It from our own Jeff Lepp. And this galaxy here is a little bit farther away than Andromeda. It's about 2.8 million light years away. And it has a size of about 51,000 light years in diameter. So it's about half the size of our own Milky Way, but very striking spiral arms, very striking feature, very, the shape of the object is really cool. This galaxy has some one, or at least one area that I'll point out here. It has a H2 region that is a star producing region, and it's down here in this neck of the woods right here. You see this bright red blob right here. That's actually an emission nebula that is analogous or akin to our own Orion Nebula. However, it is much larger in size. Orion's about 34 light years in size. This one's 1,500 light years in size, but it has similar spectrum of light coming from it as we view from Orion. So the fact that we can see, and that this particular region has been named as a separate object, is actually NGC 604. The fact that it is a nebula that we can see 2.8 million light years away is pretty astonishing. So that is Triangulum M33, again, another galaxy in our own local group. We're going to wrap up our tour here with a view of Cassiopeia. So Cassiopeia is a constellation that is in the same neighborhood as Andromeda and Triangulum. And I'm just going to jump back up here. So here we were with M31, down here to M33. Next, we're going to go up here to this squiggly looking constellation called Cassiopeia. Cassiopeia is very easy to spot. When you're out in the night sky, you see that pattern. It's very apparent that you're on Cassiopeia. So it's a very easy constellation to find. And when you find it, you can get to the Heart Nebula. And here is a picture of Cassiopeia tonight at 9 o'clock. And you can see that the Heart Nebula resides off of the tail end of the structure here of Cassiopeia. Cassiopeia, as it's coming up, and it's circumpolar. When you're looking north is when you're looking at Cassiopeia, and as it's coming up, it's going to have the shape of a W, but as it gets towards the top in the zenith, it's going to have the shape of an M, and that's how you'll be able to kind of get your bearings here. The Heart Nebula is off the tail end of this, so it's following Cassiopeia as it's moving up towards the zenith. And here's a picture of the Heart Nebula, and it's a very interesting complex structure. It's an emission nebula, and it is about 6,200 light years away, about 107 light years in size. So it's a very wide field of view object. There's a small group of stars in here in the center that are actually ionizing the gases that you see in and around the nebula. And there have been some stellar winds from these stars that have actually formed these pockets or voids that you see here and here. It's a very cool object, very striking object. I've had the opportunity to photograph that here a couple of years ago, and it was one of the more popular posts on Instagram that I've ever made. So I owe it to the Heart Nebula, a really beautiful object, and again, one that I hope you go out and look at as you're doing your observing this autumn. Here is my handy dandy chart to just kind of give you some viewing options, or at least my suggestions. Andromeda, you can see, you can look at Andromeda from using an Triangulum, using a naked eye all the way up to EAA if you want. But again, a very cool selection of objects for this time of year, and I encourage you to get out there and look. We also have some cool upcoming celestial events, so we'll go over these briefly. You have the annular solar eclipse that's coming up on October 14th. I think everybody's kind of getting primed for that, and getting their hopefully you've already located your viewing spot, and you can get to it, and that ought to be very exciting for the state of Texas. We have Moon and Saturn conjunction on the 24th, and then at the end of the month, partial lunar eclipse. So a lot of things going on with the moon, the planets, and the stars this month. Have a couple of meteor showers as well. The Draconoids and Orionids. These are all happening. Well, Orionids happening throughout the course of October and November, and then the Draconids are very short-lived in the early October. So with that, get out there and stargaze. There's going to be a lot of cool things to look at this autumn, and great opportunity, excuse to get out to the dark side, utilize it. Okay, so space observatories. Well, that's kind of strange. What's going on here? Okay, well, you remember a couple of months ago in July, I did a supplemental presentation on artificial intelligence. And as I was doing that, I noticed that, I knew a couple of space observatories, obviously the Hubble, James Webb, I've heard of Gaia, heard of a few. But as I started looking, doing research for that topic, I noticed there were a lot of them, more than I thought anyway. And I thought, well, gee, how many of these are there out there? And I just thought it would really be interesting to kind of have a cursory discussion about this. So what I want to talk about here is just first of all, why do we put observatories in space? Talk about what's out there. There's this really cool graphic that I was able to find on the web, and I want to use that to kind of tee up the kind of the big picture of all these, where are all these space observatories located? Then kind of go through a couple of graphs to kind of go by show by the numbers what we've got, and then pick out about 4 of these that I found fairly interesting and kind of do a bit of a deep dive on them. So why do we put observatories in space? So one of the reasons is we can get a better view. Certainly that applies to objects like the sun. Sometimes it's the only way we can get a view. In particular, asteroids that are close to Earth, in between the Earth and the sun, that is really the only way we can see these. We can get a clearer view, obviously. We don't have the atmosphere that we have to contend with. We don't have weather that we have to contend with. We certainly can get more viewing time, again, because you don't have daylight, or you can mitigate the daylight by orbit that you put the observatory in. Probably one of the fundamental reasons is part of the spectrum, electromagnetic spectrum, simply can't be viewed from Earth, or can't be viewed very well from Earth, because the atmosphere is blocking things like X-rays and gamma rays, infrared light, and ultraviolet light. So it's a good thing the atmosphere is doing that, because it's keeping us safe and protected. But in terms of observing, it inhibits that. So putting observatories in space for X-ray and gamma ray observation, for example, is really the only way to go. So this pictorial, I mean, I just love this diagram. Here in one snapshot, you can see pretty much all the space observatories that are out there. Not only that, you can see them in the various orbits that they're in. And so you've also got these little designations here to kind of show you what part of the spectral range each of these observatories is operating in. The observatories that you see up here are already launched. They were launched prior to 2021. And then down here, you see a list of future missions. Now, this slide is a bit dated because it still has the James Webb Telescope being on the future missions list. But for the most part, it's just a great snapshot of the observatories that are out there and what their functions are, what part of the spectral range they're examining. Here is a second piece of that diagram. This displays the spectral range that each of the space observatories are operating in, along with the resolution that they're operating in. A little bit of a busy diagram, not the easiest one to study, but nonetheless interesting. So I thought I'd include that in the discussion as well. So what I did is I took the observatories that were on that first chart, and I just put them into a spreadsheet, came up with a couple of pie graphs to kind of show you where these observatories, how these observatories are being used. So here you see a list of observatories that were launched prior to 2021. I went ahead and included the James Webb in this list because of the notoriety it's gotten, and I also had information on its orbit that I could use. So I included the James Webb in here. You have a total of 43 space observatories are out there, and again, that's according to the diagram that I looked at. I don't know if that was comprehensive or not, but I'm using that as kind of my data source. And so here you can see a couple of things that kind of stand out. There's a lot of space observatories here that are dealing with the sun, or the heliophisic spectral range, which I think is kind of a grab bag for a bunch of different sets of data and parameters that the observatory is collecting. You'll see then again infrared, X-ray, gamma ray. Again, those areas that are inhibited those spectral parts of the spectral range that are inhibited by the atmosphere. Again, you can imagine that, yeah, there'd be a lot of interest in having space observatories up there that operate in that range. So this is kind of the ones that are up there in operation. And then here is the same graph that is for those space observatories that are going to be launched post 2021. And again, heliophysics really stands out. A lot of activity in going and looking at our own sun. And again, infrared and X-ray are the two other main areas of interest. This last chart that I'll show you here is a view of all the space observatories that were launched prior to 2021, and this shows you the various orbits that the space observatories operate in. And when I first looked at the diagram, I thought, oh, that's interesting. And then I started to kind of dig into the numbers here, and it sort of got me to wondering, well, why would you put one observatory in one type of orbit versus another? So that kind of led me to this, and thought it was really interesting. In general, the choice of the orbit involves really kind of a trade-off between the goals of the mission and the technology and the budget constraints. So that just kind of as a general proposition, that's what you kind of balance. Where does it do its where does the observatory do its best for work versus what we can technically and get accomplished, and what can we afford? So low Earth orbit, which is where the Hubble was, it's a less expensive region to put a space observatory in because it's so close to the Earth. So it's less expensive, and it also allows for servicing and maintenance. So, in the Hubble, we went up there several times to change out components and whatnot, and you wouldn't be able to do that unless it was the observatory was in low Earth orbit. There's another orbit, geostationary. This orbit provides a consistent view of the same region of the Earth's surface. This is common for communication satellites, less so for telescopes. But when we go into the deep dive, I do have an example of a observatory that's in a geocentric orbit and the reasons behind that. So we'll go into that in a little bit. Polar orbit, which is the one that kind of goes up and around the poles of the Earth, that allows for a telescope to observe the entire sky over time. This is useful for surveys. Highly elliptical orbits, where it kind of comes in close to the Earth and then shoots out at a long distance away from the Earth. This is useful if you are looking at a specific part of the sky, and it allows you to just spend less time closer to Earth and around our radiation belts. So that is one of the reasons that you go into a highly elliptical orbit. And then the Lagrange points. We all heard about Lagrange point 2 with the James Webb telescope. There's also Lagrange point 1, which is on the other side, and it's actually closer to the sun. You go to a Lagrange point for a couple of different reasons. First of all, you have long periods of observing time, plus you have minimal gravity. And that minimal gravity is important because you get a more stable environment that more sensitive equipment can operate in. So if you have really delicate measurements that you're taking or you need to take, operating at these Lagrange points gives you a much more stable environment in order to conduct your experiments. You also have the ability to get continuous solar exposure. So if you're over at Lagrange point 1, you're facing the sun all the time, and you have the ability to really maximize your observing time. On the other side, on Lagrange point 2, you have the ability to operate away from the sun. And in the course of the Webb telescope, you have the shielding that keeps the sunlight away and keeps the temperature down. So those are the kind of in general, what are the logic behind the different orbits that you put a space observatory in. I thought that was kind of interesting. Okay, so let's take a look at a few here. I'm going to be looking at TESS, which is up here in that highly elliptical orbit. We're going to be looking at NEOSAT, which is in this polar orbit. We'll be looking at the Solar Dynamic Observatory, which is in the geosynchronous orbit, and I'll talk a little bit more about why they put it there. And then we'll talk about Gaia, which is in at Lagrange point 2, along with the Hubble telescope. All right, so TESS. So TESS stands for Transiting Exoplanet Survey Satellite. Its spectral range is primarily in the infrared. And again, it's in that highly elliptical orbit, so it's going out and it's looking at a specific point in the sky, rather, or a region of the sky. The United States is the primary or sole operator of this telescope. It was been in operation since 2018, and the mission here is to search for exoplanets using the transit method. And the area that this particular observatory is looking in is 400 times larger than Kepler, which I think was a previous exoplanet mission. Now, TESS is it's serving the brightest stars near our own Earth for transiting exoplanets. It is studying the mass, size, density, and orbit of a large cohort of small planets, including a sample of rocky planets in the habitable zone. And excuse me, I'm reading off my notes, but I want to make sure I get all this information out correctly. And what will be nice about TESS is that we'll be providing targets for further review by the Webb telescope and other ground-based telescopes around the world. So this is what's going on. This is a space observatory that's primary focus is on exoplanets. It's referred to as TESS. The next mission that our space observatory that I want to talk about is NEOSAT. It's operating in the optical range, and it is in polar orbit around is a polar orbit around the Earth. Canada is the operator of this telescope or this space observatory. And what this observatory is doing is it's detecting and tracking asteroids, comets, satellites, and Earth debris. So it's searching for and tracking near-Earth asteroids inside the Earth's orbit around the sun. And so because of that, these asteroids are difficult to detect from the surface of the Earth because you have that sunlight that's kind of blinding you, not allowing you to see these objects in the daylight or at twilight. So one of the main reasons early on we talked about for having a space observatory or a reason to have a space observatory is to get access and view objects that you just wouldn't be able to see from Earth. And this is a prime example of that, where these asteroids and the space debris, you just can't see it if you're down here on Earth. The next one here that would like to talk about is Gaia. It operates in the optical range, and it's out at Lagrange point 2, just like our James Webb telescope is at. It's a satellite observatory that's operated by the European Space Agency. And the mission of the Gaia Space Observatory is to map out put together a large three-dimensional map of the Milky Way. One other thing that is happening as part of the mission is there are a plethora of spectrographic or spectrophotometric measurements taken of the stars that it's surveying, and those measurements will be characterizing luminosity, excuse me, temperature, gravity, and elemental composition. So one of the reasons that I'm personally that I'm interested in this one is because this data you can actually use for photometric color calibrations when you're processing astrophotography photos. And I believe that PixInsight now has access to the Gaia database in order to do those calibrations. So I thought that was pretty cool. So that's data that is being collected that, you know, even I as a novice can take advantage of and use. So I thought that was pretty interesting. So that's Gaia. And then the last one I'll talk about is the Solar Dynamic Observatory. And as I mentioned earlier, this is in that and so this heliophysical is a spectral type. So it's gathering a kind of a grab bag of information, you know, visual, other measurements of the sun. And it's in this geosynchronous orbit. And again, the geosynchronous was primarily geared for communication satellites, but they put this observatory in the geosynchronous orbit because they have a tremendous amount of data that they're feeding back to Earth as a result of their observations. And I went back and looked at the July presentation, and yeah, indeed, you know, they're sending back about 1.5 terabytes of data a day from this observatory back to Earth, and they put it in geosynchronous orbit so that they can track the receivers for that data and make these transmissions. So they can not only do that, but they can also put it in such a geosynchronous orbit as it's able to look at the sun as well. So I thought that was really cool, and kind of provided an explanation for why an observatory would be in geosynchronous orbit. This is a USA-sponsored observatory. It's studying, its mission is to study how solar activity is created and how it drives space weather. There are three kind of areas of inquiry that this observatory is going after. So there's one area called helioseismic and magnetic imaging. And what they're trying to do here is establish the relationship between the internal dynamics of the sun and magnetic activity. A second area of inquiry is to examine extreme ultraviolet light and understand that extreme ultraviolet light's relationship with magnetic variation in the sun. And that's important because the sun's output of this type of electromagnetic energy is what heats the Earth's upper atmosphere and creates the ionosphere. So that's the second area of inquiry. And then the third has to do with the kind of the atmosphere of the sun. So they have an atmospheric imaging apparatus that is providing full disk observations of the chromosphere and the corona, and it is providing views that occur within the outer solar atmosphere. So that's SDO. Again, I think if you're going to study stars and how they operate, our own sun is a great candidate to go after. And as you saw from those pie charts, there's a lot of activity in the solar observing area. Okay, so that kind of wraps up. Just wanted to provide kind of an area that I thought was very interesting. Kind of give you a little bit of information on that. as a supplement to this presentation. Okay, so I just want to wrap up my talk tonight with the following. But between now and the end of the year, I'll be putting together the novice presentation schedule for 2024. And in order to do that, I'd really like to hear from you. I want to get from you the following. I'd like to hear from you on any topic ideas that you'd like to hear about. I'd like to also hear from you if you're interested in making a novice presentation. And I think that making a novice presentation is great for three reasons. Number one, if you're a novice and you're going to make a presentation, you really have to study the material, and it's a great way to learn, and it's a great way to retain the learning. So I encourage you to volunteer to do that for that reason alone. If you have public speaking practice that you need to make for a job or another organization, this is a great way to get practice in a kind of a low stress environment. We have audiences typically of 25 to 30 people. We do these on Zoom. It's a great way to practice, and it's a great way to get your public speaking skills improved. And the third reason is that it's just a great way to pay back to the Astronomical Society. Making a presentation, it is a great way to contribute and a great way to give back to the organization. So with that in mind, I'm leaving you with 3 email addresses here that I can be reached at. My personal one, cmorisette@yahoo.com, is probably the most fail-safe way to get in touch with me. Please note my last name ends with an E, but my email address does not have an E. So you can reach me there. You can reach me at chrism@astronomyhouston.org, or you can reach me at novice@astronomyhouston.org. The second 2 email addresses I check at least once a week. So if you don't get an immediate response, you should get one within a week. But again, I'd love to hear from you. I'd love to hear what you want to hear about next year. And I'd also would love to have any volunteers that would be interested in making a novice presentation. All right, so with that, we are at the end of our presentation for October, and I appreciate your attention, and I wish you all a good evening. Thank you very much.